Tonight, if you have the chance to look up at a clear sky, the universe has a gift for us. Silently and suddenly, you might see fleeting streaks of light, silver lines that quickly flash and then disappear into the darkness. This is the Perseid Meteor shower, one of the most beautiful and reliable of the year. And right now, it is at the peak of its performance. Welcome back to Science for Sleep. If this journey to witness the night sky's gift sparks your curiosity, a gentle tap of the like and subscribe buttons will help us continue these voyages together. And, as always, I would love to know where you are listening from in the world. Please feel free to leave a greeting in the comments so we know how far this story has traveled. In tonight's video, we will not just be watching. We will together learn the story behind these delicate streaks of light. Where do they come from? How long have they traveled? And why, for thousands of years, have humans looked up at the sky on these very nights with a sense of wonder and hope? Whether you are under a real sky or just closing your eyes and imagining one in your room, let us begin our journey together to explore the tiers of the stars. Before we journey further into the history and origin of this beautiful celestial event, let us pause for a moment to understand what it is we are actually seeing. When you witness that fleeting streak of light paint itself across the night sky, what is it? Our ancestors gave it the name shooting star or falling star, a poetic and beautiful description that captures the magic of the moment. But the reality, while less about stars, is no less magical in its own scientific way. To decode the streak, we must first learn a quiet, cosmic vocabulary. There are 3 words that describe the life of this tiny traveler, 3 distinct chapters in its very short and brilliant story: meteoroid, meteor, and meteorite. They sound similar, but each one describes a different stage of the journey. Let us begin in the cold, silent emptiness of space. Here, before it ever encounters our planet, our traveler is known as a meteoroid. This is a small, solid body, a piece of rock or ice, drifting through the solar system. The term itself is a matter of scale. If it is large, kilometers wide, we call it an asteroid. If it is a great ball of ice and dust, with a long, glowing tail, we call it a comet. But if it is small, ranging in size from a large boulder to a tiny grain of sand, it is a meteoroid. The vast majority of the particles that create the Perseid meteor shower are incredibly small, most no larger than a pebble, a pea, or a single grain of sand. They are the forgotten crumbs of the cosmos, the dusty leftovers from the formation of our solar system, or, as we will see, the debris shed by a passing comet. For thousands, or even millions of years, these tiny meteoroids travel in darkness, silent and frozen, their long journey through the void completely unseen. The second chapter of its life is brief, brilliant, and is the very reason we are telling this story. It begins the moment the meteoroid's path intersects with the Earth's. Our planet is constantly moving through space, and as it does, it sweeps up these tiny particles. When a meteoroid enters our atmosphere, traveling at an immense speed, it becomes a meteor. This is the official name for the streak of light, the shooting star itself. But here is a beautiful and counterintuitive secret. The light you see is not the rock itself burning. The meteoroid is too small and is traveling too fast to simply catch fire like a piece of wood. Instead, the light is created by the air in front of it. As the tiny meteoroid plummets into our atmosphere at speeds of up to 60 kilometers per second, it compresses the air in its path with incredible force. This extreme compression heats the air to thousands of degrees Celsius, causing the air molecules themselves to glow. The streak of light is a trail of incandescent, ionized air, a temporary, glowing scar left in the atmosphere by the passage of this tiny, high-speed intruder. The meteoroid itself is often completely vaporized by this intense heat, turning from a solid grain of sand into a puff of vapor in less than a second. It is a final, spectacular act of self-destruction, a brief and beautiful farewell. The third and final chapter is the rarest of all. Most meteoroids are small enough to be completely destroyed in the atmosphere, but occasionally, a larger, more resilient one will survive its fiery descent. If any piece of the original meteoroid survives the journey and physically strikes the ground, it is then called a meteorite. These are the true visitors from space, the rocks from another world that we can hold in our hands. They are incredibly valuable to science, as they are pristine samples of ancient material from the asteroid belt, from the Moon, or even from the planet Mars, blasted off by ancient impacts. The particles of the Perseid meteor shower, however, are far too small and fragile to ever make it to the ground. They are delicate, dusty debris from a comet, and their story always ends in that brief, beautiful flash in the upper atmosphere. They are destined to always be meteors, never meteorites. So, as you lie back and watch the sky, you can now see the story with a new clarity. What you are witnessing is the final, fleeting moment in the long life of a meteoroid, a tiny grain of cosmic dust, as it becomes a meteor, a brief and brilliant line of glowing air, before vanishing forever. It is a story, with a beginning in the cold darkness of space, a fiery middle in our protective atmosphere, and a quiet, vaporous end. We now understand that the beautiful streak of light we call a shooting star is the final, brilliant farewell of a tiny piece of cosmic dust. But the true magic of this event lies not just in what it is, but in how it happens. The light you see is not the simple act of a rock burning up, like a log in a fire. The process is far more violent, far faster, and far more elegant. It is a story of pure physics, a lesson in energy and transformation played out in a fraction of a second, 100 kilometers above your head. Let us begin with the most crucial ingredient: speed. The tiny meteoroids of the Perseid shower are not gently falling into our atmosphere. They are colliding with it at a speed that is difficult for our minds to comprehend. They travel at approximately 60 kilometers per second, that is over 200 kilometers per hour. It is a speed so immense that you could travel from one coast of the United States to the other in less than a minute. At this velocity, a tiny grain of sand, no larger than a poppy seed, carries an incredible amount of kinetic energy. The energy of motion is proportional to the square of the velocity, which means that doubling the speed quadruples the energy. At these hypersonic speeds, even a minuscule object becomes a tiny, focused bullet of immense power. Now imagine what this tiny bullet is about to hit. The Earth's atmosphere, which seems so thin and ethereal to us, is, from the perspective of a high-speed meteoroid, a dense and viscous ocean of air. As the meteoroid plunges into this ocean, it does not slice through it cleanly. Instead, it violently compresses the air directly in front of it. This is a process known as ram pressure. Think of a piston in a cylinder. When you compress a gas very quickly, it heats up. The meteoroid is a natural hypersonic piston. The compression of the air in its path is so extreme and so instantaneous that the temperature of that air skyrockets to thousands of degrees Celsius, a temperature hotter than the surface of the sun. And it is this superheated, compressed pocket of air that creates the spectacle. This intense heat does two things. First, it completely vaporizes the solid meteoroid itself. The grain of sand does not burn. It is instantly sublimated, turning from a solid directly into a puff of superheated gas, its physical form erased in a millisecond. Second, and more importantly, this intense heat rips the electrons away from the atoms of the air itself. The molecules of nitrogen and oxygen in the atmosphere are torn apart, their electrons stripped away, creating a glowing, incandescent channel of plasma. The streak of light that we see, the meteor, is not the rock. It is this trail of glowing, ionized air, a temporary, luminous scar left in the upper atmosphere. It is the atmosphere's own brilliant reaction to the violent passage of the intruder. The different colors we sometimes see in meteors are the spectral signatures of the elements being vaporized, both from the meteoroid and the air. Sodium atoms, for example, produce a bright orange-yellow glow. Magnesium creates a beautiful blue-green light. Nitrogen and oxygen in our own atmosphere tend to glow reddish. The Perseids are known for their speed and brightness, and often leave behind persistent, glowing trails, or trains, which are the lingering columns of ionized air slowly fading as they cool and recombine. It is a final, beautiful act of physics, a cold, dark piece of a distant comet, transforming its immense kinetic energy into a brief and silent line of light, a final, graceful bow before it vanishes forever. Every great meteor shower, every reliable and beautiful display in our night sky, has a source. These streams of dust are not random. They are the children of a parent, a great celestial body that has traveled the same path for eons, leaving behind a trail of cosmic crumbs. For the Perseids, that parent is a magnificent and formidable comet, a giant of our solar system known as Comet 109P, Swift-Tuttle. Its story, in our human terms, begins in the summer of 1862. Two American astronomers, Lewis Swift and Horace Tuttle, working independently just a few days apart, each spotted a new, faint, and fuzzy object in the night sky. They had discovered a new comet. It was named in their honor, a permanent celestial monument to their patient skywatching. But the comet itself is far, far older than its name. It is an ancient traveler, a relic from the very birth of our solar system, 4.6 billion years ago. Comet Swift-Tuttle is not a small object. Its nucleus, the solid core of the comet, is estimated to be about 26 kilometers, or 16 miles, in diameter. This makes it more than twice the size of the asteroid that is believed to have wiped out the dinosaurs. It is a true giant, one of the largest known comets in a short period orbit. It is, in essence, a small, dark, and icy mountain, hurtling through the emptiness of space. Like all comets, Swift-Tuttle is a dirty snowball. Its core is a loose conglomeration of water, ice, frozen gases like carbon dioxide and methane, and a large amount of rock and dust, all held together in a fragile, porous structure. For most of its long journey, as it travels through the cold, outer reaches of the solar system, it is a dark and dormant object, almost impossible to see. But its orbit is a long and highly elliptical one, a great, stretched-out loop that takes 133 years to complete. This orbit carries it far out beyond the path of Pluto, into the cold twilight of the Kuiper Belt, and then brings it swinging back in, close to the Sun, even closer than the Earth's own orbit. And it is during this close approach to the Sun that the sleeping giant awakens and puts on its spectacular show, the very show that creates the Perseid Meteor shower. It is a story of fire and ice, a quiet drama that has been repeating, once every 133 years, for millennia. For most of its 133-year journey, Comet Swift-Tuttle is a ghost, a silent and frozen mountain of ice and rock, traveling through the profound cold and darkness of the outer solar system. It is a world in a deep and long hibernation, but as its great, elliptical orbit brings it back towards the inner solar system, back towards the warmth and light of the Sun, a magnificent transformation begins. The sleeping giant starts to awaken. As the comet crosses the orbit of Jupiter and then Mars, the Sun is no longer a distant, brilliant star. It becomes a powerful engine of heat and radiation. This energy begins to warm the comet's dark, icy surface, but in the vacuum of space, the ice does not melt into liquid water. Instead, it undergoes a more direct and beautiful process called sublimation. The ancient water ice, frozen for billions of years, turns directly from a solid into a gas, skipping the liquid phase entirely. This process is not gentle. As the surface heats, jets of water vapor and other frozen gases erupt from the nucleus like cosmic geysers. And as these gases burst forth, they carry with them the dust and small rock particles that have been trapped within the ice for eons. These are the primordial crumbs of the solar system, released from their long imprisonment. This cloud of gas and dust, energized by the Sun, forms a vast glowing atmosphere around the comet's solid nucleus. This is called the coma, and it can grow to be hundreds of thousands of kilometers in diameter, larger than the planet Jupiter. The Sun's influence does not stop there. The constant stream of charged particles from the Sun, the solar wind, and the pressure of sunlight itself begin to push on this newly formed coma. This force sweeps the gas and dust back, away from the sun, creating the comet's most iconic feature, its magnificent, glowing tail. In fact, comets typically have two tails: a straight, bluish tail made of ionized gas, which always points directly away from the sun, and a broader, curved, whitish tail made of dust, which tends to follow along the comet's orbital path. With every close pass of the sun, Comet Swift-Tuttle loses a tiny fraction of its mass, shedding tons of this ancient dust and ice into space. But it does not just leave this material behind in one spot. It spreads it out, like a celestial gardener scattering seeds, along its entire 133-year orbital path. Over thousands and thousands of years, after countless journeys around the sun, this has created a vast, diffuse, and almost invisible river of dust, a great elliptical stream of particles that permanently marks the comet's highway through the solar system. And it is this ancient, ghostly river of dust that is the true source of the Perseid meteor shower. The great comet Swift-Tuttle, in its magnificent, sun-drenched awakening every 133 years, is a spectacle of immense beauty. But the true gift it gives to us, the one we can witness annually from our own backyards, is not the comet itself, but the ghost it leaves behind. With every fiery pass around the sun, it sheds a small part of its ancient heart into the void, a trail of dust and ice particles that marks its long and lonely path through the solar system. This is not a temporary trail that dissipates quickly like the wake of a boat on water. In the near-perfect vacuum of space, this debris continues to travel, following the same great elliptical orbit as its parent comet. Over thousands and thousands of years, after countless journeys around the sun, this shed material has formed a vast, diffuse, and almost entirely invisible river of dust. It is a permanent feature of our solar system, a great elliptical stream of particles that traces the comet's highway through space. It is wider in some places, denser in others, a ghostly echo of the comet's long and storied history. And once every year, in the middle of summer, in the northern hemisphere, the Earth, in its own, much more circular orbit around the sun, must cross this ancient river of dust. This is the origin of the Perseid meteor shower. The event is not caused by particles randomly falling onto our planet. It is a predictable and beautiful consequence of our own planet's journey. For a few weeks, every July and August, the Earth sails directly through the debris stream left behind by Comet Swift-Tuttle. Imagine driving your car through a light, scattered swarm of insects on a summer evening. Each insect that hits your windshield creates a tiny streak. Now, imagine your car is the planet Earth, and the insects are ancient grains of cometary dust, and you begin to get a sense of the beautiful and gentle collision that is a meteor shower. The particles in this stream are not densely packed. The space between each grain of dust is vast, often many kilometers. We are not flying through a thick cloud, but through a very sparse, almost ethereal stream. But because the Earth is moving so fast, at about 30 kilometers per second, and the dust itself is also moving on its own orbit, the combined collision speed is immense. And it is this high-speed encounter that transforms these tiny, silent grains of dust into the brilliant, fleeting streaks of light that we call shooting stars. We are not just seeing a random event, we are witnessing our own planet interacting with the physical memory, the ghostly, dusty echo of a great comet's many past journeys. As our Earth sails through this ancient, ghostly river of cometary dust, the particles enter our atmosphere from a generally parallel direction. This creates a beautiful and predictable illusion, a trick of perspective that gives every meteor shower its name and its home in our night sky. This is the phenomenon of the radiant. Imagine you are driving a car at night through a gentle, steady snowstorm. As you look out through your front windshield, the snowflakes do not seem to be falling randomly. Because you are moving forward into the storm, the flakes appear to stream towards you from a single point directly ahead, a vanishing point on the horizon. They seem to radiate outwards from this central spot, streaking past you on all sides. The snowflakes are, of course, falling in parallel paths, but your own motion creates the illusion that they are all originating from a single point in the distance. Now, let us scale this analogy up to the cosmos. Your car is the planet Earth, traveling on its vast, orbital highway around the sun. The snowstorm is the sparse, wide stream of dust left behind by Comet Swift-Tuttle. As the Earth plunges into this stream, the tiny meteoroids all enter our atmosphere from roughly the same direction. And just like the snowflakes, from our perspective here on the ground, their fiery streaks all appear to radiate outwards from a single point in the night sky. This point is the radiant of the meteor shower. For the Perseids, this radiant point lies within the boundaries of a famous and ancient constellation, the constellation Perseus, the hero, and that is how the shower gets its name. The meteors are not, of course, coming from the distant stars of Perseus. Those stars are trillions of kilometers away, unimaginably distant. The meteors themselves are burning up only about 100 kilometers above our heads. But due to the beautiful and reliable geometry of our orbit, from our vantage point in mid-August, that radiant point happens to lie in the direction of Perseus. The constellation itself is a beautiful sight, nestled in the rich, starry river of the Milky Way, near the distinctive W shape of Cassiopeia. And it carries with it one of the great stories of Greek mythology. Perseus was the heroic son of Zeus, the slayer of the Gorgon Medusa, whose gaze could turn men to stone. He was the rescuer of the princess Andromeda, whom he saved from a terrible sea monster. The constellation is often depicted as the hero, holding the head of Medusa, whose eye is marked by the famous variable star, Algol. And so, for thousands of years, as our ancestors watched these streaks of light, they saw them as originating from the celestial hero. It is a beautiful and poetic connection. The tears of a saint in one culture, the fiery trail of a hero in another. It is a very human thing to do, to look up at the vast, impersonal workings of the cosmos and to weave our own stories, our own meanings, into its fabric. The radiant is a simple trick of perspective, but it gives the meteor shower a name, a character, and a place in the great mythological map of our night sky. It reminds us that science and story are not separate things, but are two different languages we use to describe the same profound wonder. The name Perseids, linking the meteor shower to the great hero of Greek mythology, gives the event a beautiful and timeless quality. But the history of our relationship with these falling stars is far older and more literal than the myths of the gods. For as long as humans have looked up at the night sky with curiosity, they have witnessed this reliable, annual display. And in a few precious instances, across different cultures and different centuries, they took the time to write it down, leaving us a faint, historical echo of their wonder. This is the forgotten history, the ancient records of the Perseid meteor shower. Our journey to find the first written account of this event takes us far from ancient Greece, to the other side of the world, to the meticulous and patient sky watchers of Han Dynasty China. In the year 36 AD, in the official court records, a Chinese astronomer made a simple but profound entry. He noted that in the 7th month of the year, more than 100 meteors flew thither in the morning. This is the earliest unambiguous historical record we have of the Perseid meteor shower. Let us take a moment to imagine that scene. A court astronomer, whose job it was to watch the heavens for omens, for changes, for anything that might affect the destiny of the empire, stands on a tower in the pre-dawn hours. The world is silent. There is no light pollution, no city glow to wash out the stars. The sky is a deep, profound black, filled with a density of stars we can barely imagine today. And in that deep silence, the sky begins to weep light. Not one or two shooting stars, but dozens, then scores, a steady and beautiful rain of light, all appearing to stream from the same region of the sky. He would not have known about Comet Swift-Tuttle. He would have had no concept of the Earth passing through a stream of cosmic dust. To him, this was a celestial event, a message from the heavens. He did his duty. He observed, He counted, and he recorded it with a simple, factual elegance: more than 100 meteors. This single, quiet sentence, preserved for nearly 2,000 years on ancient scrolls, is a bridge in time. It is a testament to a shared human experience, the simple, universal act of looking up at the night sky in awe. For many centuries after, the historical record of the Perseids is sparse. The shower undoubtedly continued its annual performance, a reliable feature of the late summer sky. But it was not until the 19th century that it was formally identified as a recurring annual shower. In the 1830s, the Belgian astronomer Adolphe Quetelet was the first to connect the August meteors to a specific date and radiant point in the constellation Perseids. He established it as a predictable annual event, moving it from the realm of random omens into the predictable clockwork of celestial mechanics. It was only a few decades later, following the discovery of Comet Swift-Tuttle in 1862, that the Italian astronomer Giovanni Schiaparelli made the final, brilliant connection. He calculated the orbit of the newly discovered comet and realized, with a flash of insight, that it was a perfect match for the orbit of the Perseid meteoroid stream. The puzzle was complete. The parent of the Perseids had been found. The shooting stars of August were not just random cosmic dust. They were the children of a specific and known comet. The ancient records of the Chinese, the medieval legends of Europe, and the modern calculations of celestial mechanics had all converged to tell a single, coherent story, a story written in the faint, fiery trails of dust left behind by a great and lonely traveler. While the astronomers of ancient China were making their quiet, factual records of the August meteors, another, far more poetic and poignant story was taking shape on the other side of the world. In medieval Europe, the Perseid meteor shower became entwined not with a celestial hero or a scientific observation, but with the story of a Christian martyr, a man of faith whose fiery end became a legend written in the night sky. This is the story of the tears of St. Lawrence. To understand this legend, we must travel back to the heart of the Roman Empire, in the 3rd century A.D. Lawrence was one of the 7 deacons of Rome, a man entrusted with the care of the church's treasury, and, more importantly, with distributing alms to the poor and the needy. During the persecution of Christians under the Emperor Valerian, the Pope was executed, and Lawrence, as the church's archdeacon, was ordered by the prefect of Rome to hand over all the church's riches within 3 days. The legend tells that Lawrence did not panic. He spent those 3 days gathering not gold and silver, but the city's poor, the crippled, the blind, and the suffering. On the 3rd day, he presented this crowd of people to the prefect and declared, "These are the true treasures of the church." The prefect, enraged by this act of defiance and piety, ordered Lawrence to be executed in a slow and agonizing manner. According to the ancient tradition, he was martyred by being roasted to death on a giant gridiron. The date of his martyrdom was August 10th, 258 AD. And here, the threads of history, faith, and astronomy begin to weave together. For centuries after his death, the people of medieval Europe noticed that in the days surrounding the anniversary of his martyrdom, on and around August 10th, the night sky would come alive with a shower of falling stars. In the deeply religious and symbolic worldview of the time, this could not be a coincidence. The connection was immediate and powerful. The shooting stars, these brief, fiery streaks that fell from the heavens, came to be known in the popular folklore of Catholic countries as the Lacrimae Sancti Laurentii, the tears of St. Lawrence. They were seen as the fiery tears of the saint, shed in his agony, falling from the heavens each year as a celestial memorial to his sacrifice. The night of August 10th became a time of quiet contemplation, a night to watch the sky not just for its beauty, but for a sign of faith, a reminder of a story of courage and devotion. This legend transformed the meteor shower from a simple astronomical event into a deeply emotional and spiritual one. It gave the silent, impersonal streaks of light a human story, a name, and a meaning that resonated with the hearts of the people who watched them. It is a beautiful example of how humanity has always looked to the heavens to find a reflection of its own stories, its own values, and its own deepest beliefs. The science, as we now know, tells a different story, one of cometary dust and orbital mechanics. But the legend of St. Lawrence's tears is no less true in a cultural sense. It is a testament to our enduring need to find poetry in the cosmos, to weave our own human narratives into the grand, silent tapestry of the night sky. We have spoken of the great comet, of the geometry of orbits, and of the long arc of human history. But now, let us zoom in. Let us quiet our minds and focus our attention on a single, solitary character in this grand celestial play. Let us tell the story of one single grain of dust. Its life began billions of years ago, in the great, cold, swirling nebula that would one day become our solar system. It was a tiny speck of silicate mineral, perhaps, or a flake of carbon, forged in the heart of a long-dead star and cast out into the void. For an age, it drifted in the primordial cloud, until it was gathered up, along with countless others, into the growing, icy body of what would become Comet Swift-Tuttle. For the next 4.5 billion years, its existence was one of profound stillness and cold. It was a prisoner in a tomb of ice, locked deep within the comet's nucleus. It traveled on a great, looping journey through the darkness, a silent passenger on a mountain of ice. It felt the distant, faint light of stars it would never visit. It endured the absolute zero of deep space. It was a part of a great, sleeping whole, its individual existence meaningless. Then, perhaps a few thousand years ago, during one of the comet's fiery passes around the sun, its long imprisonment came to an end. As the comet's surface heated and sublimated, the ice that held our dust grain in place vaporized. In a gentle, chaotic puff of gas, it was released from the nucleus and pushed out into the comet's magnificent, glowing tail. For a brief time, it was part of the spectacle, a tiny, glittering mote in a river of light. But as the comet moved on, pulling away from the sun and returning to the cold darkness, our dust grain did not return with it. It was left behind, liberated from its parent, and it began a new, independent life. It was now a meteoroid, a lonely traveler. It was no longer bound to the comet, but it was still bound by gravity to follow the same great, elliptical path, the ghostly highway that the comet had carved through the solar system. And so it traveled, for centuries, for millennia. It was a silent, solitary journey. It tumbled slowly in the sunlight, a tiny, forgotten speck. It survived the gentle pressure of the solar wind. It narrowly missed collisions with other, larger pieces of debris. It was a quiet existence, a long and patient orbit, waiting for a destiny it could not know. And then, tonight, on this very night in August, its long, lonely path finally intersected with the path of a much larger traveler, the planet Earth. The encounter was not a choice. It was an inevitability, a meeting of two orbits calculated by gravity billions of years ago. As the Earth, in its great, swift journey, swept through this part of space, our tiny grain of dust was in the way. Its final journey was brief and violent. It plunged into the upper atmosphere at 60 kilometers per second. In a fraction of a second, the friction and compression of the air heated it to thousands of degrees. The tiny, ancient grain of dust that had survived for billions of years, that had traveled from the birth of the solar system, was completely and utterly vaporized. It became a brief, brilliant streak of light, a final, silent farewell, a tear of a star that was, in the end, just a memory of a comet written in the sky for you. So now, as you lie back, either under a real, star-dusted sky or in the quiet theater of your own mind, you are ready to watch the show. You know the story of the great comet, the history of the shower, and the final, fiery journey of a single grain of dust. But what will you actually see? The Perseid Meteor shower is a patient performance, a quiet and beautiful display that rewards a calm and attentive gaze. Most of the meteors you will see will be faint and incredibly fast. They are not slow, majestic fireballs arcing gracefully across the entire sky. They are quick, delicate streaks of light, like a brief silver pencil stroke on the dark canvas of the night. They appear and disappear in less than a second, a fleeting hello and goodbye. You might see one in the corner of your eye, a flash of motion so quick you might question if you saw it at all. This is the typical Perseid, born from a particle no larger than a grain of sand, a silent and beautiful death. But the Perseids are famous for more than just these faint streaks. They are renowned for their high number of fireballs. A fireball is not a different kind of object. It is simply a very, very bright meteor. A meteor that is brighter than the planet Venus, the brightest star-like object in our night sky. These are the showstoppers, the dramatic soloists in the quiet celestial symphony, and they are born from slightly larger particles, meteoroids, perhaps the size of a pebble or a marble. When a particle this size hits the atmosphere at 60 kilometers per second, the energy it releases is immense. The resulting streak of light is not faint and silver, but brilliant and often colorful. A fireball can be so bright it momentarily casts faint shadows on the ground. It might flash with a brilliant green or a deep red, the spectral signatures of the different minerals in the meteoroid and the superheated air around it. And unlike their fainter cousins, fireballs often leave behind a spectacular and ghostly aftereffect, a persistent train. This is not a smoke trail. It is a glowing, ethereal ribbon of ionized air, a lingering scar in the upper atmosphere that can remain visible for several seconds, or in rare cases, for several minutes after the fireball itself has vanished. You might see it twist and contort, caught in the high-altitude winds, a silent, shimmering ghost of the meteor's fiery passage. Seeing a fireball is a matter of luck and patience. You might watch for an hour and see none, and then be rewarded with a brilliant, sky-splitting streak that takes your breath away. It is a reminder that even in a predictable cosmic event, there is still room for surprise, for a moment of unexpected and breathtaking magic. And so, with the story of the cosmos fresh in your mind, you are ready to become an observer, a quiet participant in this ancient celestial display. The science of watching a meteor shower is beautifully simple. It requires no expensive equipment, no complex calculations, and no specialized knowledge. It requires only three things: a dark sky, a comfortable place to rest, and a patient, open mind. This is not an act of searching. It is an act of receiving. It is a form of celestial meditation. First, you must find your sanctuary of darkness. The greatest enemy of a meteor shower is the bright, ambitious light of our own civilization. The glow from cities and towns can wash out the delicate light of all but the brightest fireballs, hiding the subtle, beautiful majority of the show. So, if you can, find a place away from the city lights. A quiet park, a field, a remote beach, or even just a dark corner of your own backyard. The further you can get from the artificial glare, the more the universe will reveal itself to you. Next, make yourself comfortable. This is not a performance you stand and watch. This is an experience you sink into. Bring a blanket or a reclining chair. Lie down on your back, so your gaze is naturally turned upwards towards the vast expanse of the sky. You do not want to crane your neck. You want to be in a state of complete physical relaxation, your body at rest, so your mind and your eyes can be free to wander. Now comes the most important and perhaps most difficult part in our modern, hurried world: patience. Your eyes need time to adapt to the darkness. It can take 20 to 30 minutes for your pupils to fully dilate and for your eyes to reach their peak night vision sensitivity. During this time, resist the urge to look at your phone. The bright light from the screen, even for a second, will reset your night vision, and the patient process of adaptation will have to begin all over again. Use this time to simply be still. Listen to the quiet sounds of the night around you, the gentle whisper of the wind, the distant chirp of a cricket, the slow, steady rhythm of your own breathing. This is the prelude to the show, a quiet and necessary overture. Once your eyes have adapted, the true observation begins, And the secret to seeing meteors is not to look for them. Do not stare intently at one single spot in the sky, especially not directly at the radiant in the constellation Perseids. If you do, you will have a very narrow field of view, and will miss the majority of the meteors, which can appear anywhere in the sky. Instead, relax your gaze. Look up at a wide, open patch of the sky, perhaps about halfway up from the horizon. Let your eyes go soft and unfocused. You are not hunting for streaks of light. You are simply allowing the sky to present them to you when it is ready. Let your mind be as open and as vast as the sky you are watching. Let go of the expectation of seeing something every second. There will be long moments of quiet, where nothing happens but the slow, majestic turning of the stars, and that is part of the beauty. In those quiet moments, you are not just waiting, you are observing the universe in its natural, peaceful state. And then, in the corner of your eye, a faint, quick streak will appear. And then another. And then perhaps a brilliant fireball will paint a brief, glorious line across the darkness. Each one is a gift, a momentary and unrepeatable event. Do not try to count them or analyze them. Simply acknowledge them, a quiet thank you to the cosmos, and then return your gaze to the quiet darkness, waiting for the next one. This is the meditation of the meteor shower, a practice of patience, of quiet observation, and of finding joy in the fleeting, beautiful moments that the universe chooses to share. As you lie back, watching these gentle, fleeting streaks of light, it is easy to see this event as one of pure and harmless beauty. And for us, here and now, it is. The tiny dust particles that create the Perseids pose no threat to us on the ground. They are a gift from the cosmos, a quiet and beautiful spectacle. And yet, the story of the Perseids has a slightly more dramatic and sobering side. It is a story that involves the parent of all this dust, the great Comet Swift-Tuttle itself. Because of its immense size and its orbital path, which directly crosses the orbit of the Earth, Comet Swift-Tuttle is officially classified by astronomers as a potentially hazardous object, or PHO. This is a designation given to any near-Earth asteroid or comet that is large enough to cause significant regional or global damage, and whose orbit brings it within a certain close distance of our own planet. And Swift-Tuttle fits this description perfectly. Let us remember the scale of this object. At 26 kilometers in diameter, its nucleus is a mountain of ice and rock, far larger than the object that ended the age of the dinosaurs. An impact from a body of this size would not be a regional disaster. It would be a global cataclysm, an extinction-level event. And every 133 years, this colossal object, on its long journey around the sun, crosses our path. This fact has led some in the past to label Swift-Tuttle as the single most dangerous object known to humanity. But here, in this quiet space, it is important to separate the dramatic potential from the scientific reality. And the reality is a story of profound reassurance, a testament to the power of mathematics and patient observation. The reason we know Swift-Tuttle is a potentially hazardous object is the very same reason we know that it is not, in fact, a threat. Astronomers have been tracking this great comet for over a century and a half. With every observation, with every new data point, our understanding of its precise orbital path becomes more and more refined. And the calculations are now incredibly certain. Scientists have mapped its trajectory for thousands of years into the future. And the conclusion is definitive. Comet Swift-Tuttle poses absolutely no risk of colliding with the Earth for at least the next 2,000 years. Its orbit is stable, predictable, and while it crosses our path, it will not do so when we are in the same place at the same time. Its next close approach to Earth will be in the year 2126. It will pass by, at a comfortable and completely safe distance of about 23 million kilometers, or about 60 times the distance to the Moon. It will be a spectacular sight in our great-grandchildren's sky, a brilliant comet visible to the naked eye, but it will pose no danger. The knowledge that allows us to identify a potential threat is the very same knowledge that allows us to find peace in its predictability. we can watch the beautiful children of the comet, the Perseid meteors, fall through our sky tonight, not with fear, but with a quiet and informed sense of wonder, secure in the knowledge that their great and giant parent will keep its safe and respectful distance. As we lie here, watching the silent fall of these ancient dust particles, it is easy to see them as something separate from us, as visitors from another world. They are the children of a distant comet, travelers from the cold, dark reaches of the solar system. They are made of ice and rock and dust. We are made of flesh and bone and thought. We seem to be fundamentally different, but the deepest and most beautiful truth that science has revealed to us is that the division between the sky and the self is an illusion. The universe is not a collection of separate things. It is a single, interconnected story, and we are all written in the same ink. Let us trace our own origins back, just as we trace the journey of the dust particle. The atoms in your body, the carbon that forms the backbone of your DNA, the oxygen you are breathing in this very moment, the calcium in your bones, where did they come from? They were not created here on Earth. With the exception of the very lightest elements like hydrogen, which were formed in the Big Bang, every other atom that makes you, you, was forged in the heart of a star. Billions of years ago, a massive star lived and died in a spectacular supernova explosion. In its final, fiery moments, it created the heavier elements and scattered them across the galaxy like seeds. This stardust then mingled with vast clouds of primordial hydrogen gas, the very same kind of great, cold nebula that gave birth to our comet, Swift-Tuttle. From this shared cloud of gas and stardust, our solar system was born. The sun, the planets, the moons, the asteroids, and the comets all coalesced from the same spinning disk of primordial material. The very same silicate minerals that make up the grain of dust that becomes a Perseid meteor are the same silicate minerals that make up the rocks beneath your feet. The same water ice, locked away in the heart of the comet, is the same kind of water that fills our oceans and flows in our veins. The same complex carbon molecules that astronomers have detected in the tails of comets are the very same kind of molecules that form the foundation of all life on Earth. There is no fundamental difference between the stuff of the heavens and the stuff of the Earth. We are all made of the same stardust. The comet and you are distant cousins, born from the same ancient cosmic cloud. And so, when you watch a Perseid meteor streak across the sky, you are not just witnessing a random astronomical event. You are witnessing a family reunion. A tiny, long-lost piece of our shared primordial heritage is returning home, announcing its arrival in a brief and brilliant flash of light. It is a quiet reminder that we are not just living on the Earth. We are a part of the cosmos, a way for the universe to look up and wonder at itself. The silent, falling star is a whisper from our own deep past, a connection that bridges the vastness of space and the quiet intimacy of a single human breath. And so, our quiet journey through the night comes to a close. We have followed the story of the Perseids from its fiery birth in the heart of a long-dead star, to its long, frozen slumber in the nucleus of Comet Swift-Tuttle, and finally, to its brief and brilliant farewell in our own atmosphere. We have seen how history, faith, and science have all looked up at this same celestial display and woven their own unique stories around it. From the factual records of ancient Chinese astronomers to the poignant medieval legend of a saint's fiery tears. This annual shower is more than just a beautiful spectacle. It is a bridge in time, a shared experience that connects us not only to the deep, cosmic past, but to the long, unbroken chain of human curiosity. For thousands of years, on these same quiet August nights, our ancestors have laid back and watched this very same sky, feeling the same sense of wonder and awe that we feel tonight. They did not know about comets or orbital mechanics, but they knew the magic of a falling star. And in that shared experience, we find a profound and gentle connection to all who have come before us. There is a common tradition, a soft piece of folklore that has survived into our modern age, that when you see a shooting star, you should make a wish. It is a lovely, hopeful thought. And perhaps, in a scientific sense, it is not so far from the truth. For what is a wish but a moment of focused hope, a quiet desire for order and peace in a chaotic world? And what is a meteor but a tiny piece of the very stardust that over billions of years coalesced to form our planet, our oceans, and eventually, us? The wish and the star are made of the same fundamental hope for existence. So tonight, as you continue your watch, or as you simply let these stories drift through your mind on the edge of sleep, let that be your final thought. When you see that next fleeting streak of light, know that you are witnessing the final moment of a billion-year journey. Send with it a quiet thought of peace, a gentle wish for yourself and for the world. And then, let it go. Let the vast, silent, and patient rhythm of the cosmos be your comfort. Let the quiet darkness of the night sky hold you. And let the gentle, falling tears of the stars be the lullaby that carries you, finally, into a deep and restful sleep. Good night.